So we are discussing how to design low pass and high pass filter by placing poles and zeros. Okay. And further, to determine the transfer function or impulse response in Z domain. So we have seen that there are two frequencies. One is at low frequency, that is omega is equal to 0, and at high frequency, omega is equal to pi. So, and corresponding value of Z, okay, we have calculated using this formula. Okay, when omega is equal to 0, that time Z is equal to 1, omega is equal to pi, that time Z is equal to minus 1. So these are the two frequency points or the value of Z which will be used to design or locate pole or zeros according to the low pass or high pass filter. So in low pass filter, we want that at low frequency or zero frequency, pole should be located, and for high pass filter, the pole should be located at omega is equal to pi, at that is at Z is equal to minus 1. So we have seen these characteristics that the top three figures represents examples of low pass filter where poles exist at the right half of the Z plane, right half of Z plane. Okay. And zeros are left half of the Z plane because Z is equal to minus 1 in case of low pass filter. Omega is equal to pi. So this should be the zeros, okay, because it makes the gain low at zeros, and at poles it makes the gain high. So this is the low pass filter Z plane, and lower one is the high pass filter Z plane where it is just folded. Okay. So that means pole should be at the left half of Z plane, okay, and zero should be right half of the Z plane. Okay. So this thing we have discussed. Now coming to the example. We are considering this example that transfer function is 1 minus a divided by 1 minus az inverse. Okay. So I have mentioned here that you can see the diagram or frequency response. Okay. That h omega or h e to the power j omega is same thing. H of e to the power j omega means hz, or that is simply written as h of omega, y axis. So there are two transfer functions. One is h1 omega, another is h2 omega. First discuss h1 omega or h1z. So you can see that h1z is having transfer function 1 minus a divided by 1 minus az inverse. Okay. Now what is the behavior at different frequencies? Omega is equal to 0 means you see that z is equal to 1. That is e to the power j omega. E to the power j omega, omega 0. So z is equal to 1. And if you put z is equal to 1 in this equation, okay, so what value it is becoming? That is, in place of z inverse, we write 1 by 1, that is same thing. Z is equal to 1, or z means z inverse. Z inverse is also equal to 1. So it means 1 minus a divided by 1 minus a is is constant, is simply 0.9. So this 1 minus A cancel out. So it makes unity gain. Okay. So we see gain is unity at frequency omega is equal to 0. Omega is equal to 0, gain is 1. Okay. Now, and since it is low pass filter, so gain should be 1 at low frequency. Now consider higher frequency, that is omega is equal to pi. And what is the gain? So omega is equal to pi corresponds to z is equal to minus 1. Okay. So z is equal to minus 1 means in place of z inverse we write minus 1. So 1 minus of minus 1, that means 1 plus a. So the value becomes 1 minus a divided by 1 plus a. And 1 minus a is 0.1. Okay. And 1 plus a means 1.9. So it is very low value. Okay. So that's why we get some value not 0 of H1 omega. Okay. That is the solid one graph. Solid one graph having some non-zero value, although very low, and which is at high frequency, that is omega is equal to pi. Okay. So it has one pole, okay, at z is equal to a, or z is equal to 0.9, that is near to the unit circle. Okay. So and also 0 is there at z is equal to 0. If you put z inverse by 1 by z, so that 1 by z term, that z term will go into the numerator. So that makes that 0, okay, at z is equal to 0. Okay. So this is one transfer function h1z. Okay. Now we can add one more zeros, okay, in this case, in this transfer function. Okay. And so that the frequency response can be made more attenuated, okay, at higher frequency. Okay, that means H2 omega, we will see at omega is equal to pi, it is absolutely 0. Okay, another transfer function which is also a low pass filter, at gain is 0 at omega is equal to pi. So how it is designed? So it is given in the next figure, next slide, that in this case we consider H2Z, that is having transfer function 1 minus a divided by 2 into adding 1 0, okay, 1 plus z inverse, okay, 1 plus z inverse adding 1 0, and there is the same term in the denominator, that is 1 minus az inverse. Just we are adding 1 0 here and slightly changing the gain. Okay. So what is the values, the gains for different frequencies? So omega is equal to 0 means z is equal to 1. Okay. So we put the values z is equal to 1, z is equal to 1. So it becomes what? 1 minus a into 1 plus 1, that is 2, by 2 divided by 1 minus a. So it is equal to 1. So unity gain is there at low frequency, omega is equal to 0, as because it is low pass filter. Similarly, at omega is equal to pi, it means z is equal to -1, okay, because e to the power j omega, omega is equal to omega is equal to pi, so that means z is equal to -1. So in that case, the transfer function becomes 1 minus a into the value. If we put z is equal to -1, that means z inverse is -1, so 1 minus 1 is 0, so it is multiplied with 0, so we get 0 gain. So we can see that here 0 was not present in the previous case. That corresponds to a little bit of gain, a little gain at having value this 0.1 by 1.9. But if you further add one more 0 to the transfer function, it provides totally gain 0 at that value. So it is a much better filter. It is a much better low pass filter if you add 0, okay, to that transfer function. So this is the role that if you add 0 or poles to a transfer functions, then its behavior is changed or modified. Okay? So I have written here that more 0 introduces more loss. Okay? This is because 0 actually corresponds to makes the functions low or very low amplitude or 0. Okay? Now consider one transfer function. Okay? That is a transfer function of high pass filter. So it is written that we can obtain simple high pass filters by folding the pole zero locations of the low pass filters about the imaginary axis. Okay? So thus we obtain the system function as the gain will remain same, 1 minus a by 2. It is not dependent on, it is a constant. Okay? Now since it is folded, so the value of the poles and zeros will be replaced. So here we see that it was 1 plus z inverse, now it is 1 minus z inverse, because we just changing the z axis from positive to negative, so it becomes 1 minus z inverse. It is folding. Okay, z is folded, so z in place of plus z, it is now minus z, so we can write here at 1 plus az inverse. So in this case you see that if frequency omega is equal to 0, it means z is equal to 1. So h3z is how much value? That is 1 minus a divided by 2 into z is equal to 1, means these functions become 0. So it is 0 gain at low frequency. Low frequency, that is omega is equal to 0. It is 0 gain. That corresponds to high pass filter. Similarly, for higher frequency, it corresponds to z is equal to minus, at omega is equal to pi. That means z is equal to -1. So it becomes 1 minus a into 2 divided by 2 into 1 minus a, that is unity gain. So it is high gain. So the next graph is that one. It is a graph for high pass filter. Okay, it is sharply increasing. Okay, at 0 it is 0 gain. At high frequency or pi it is gain 1. Okay, and right side it is the phase characteristics. Okay, phase characteristics of the filter. Okay. So there are also phase characteristics. It is this one. Okay. It is gain is, you see, you can, gain is, when gain is changing, the phase is also changing. Okay, when gain is changing, phase is changing. Similarly here also gain is changing and phase is changing. Okay. So like that. So these are the concepts of the poles and zeros, how we can select poles and zeros and design the filter. Okay, so how you select the poles and zeros, that is called frequency selective filter. Okay, and that is based on locating the poles and zeros. So now we consider several examples. We'll see that a two-pole low-pass filter has the system function. A two-pole low-pass filter has the system function is this: okay? B0 by 1 minus Pz inverse. Determine the values of B0 and P such that the frequency response H omega satisfies the condition H0 is equal to 1, and that means at omega is equal to 0, the gain is 1. At omega is equal to pi by 4, that is magnitude square. Magnitude square of the gain is half. Okay. So this is the characteristics and how we will solve it. Just let's just look into the slide. So omega is equal to 0 means A is 0, Z is equal to how much? Z is equal to 1. So in this equation we put Z is equal to 1. So it becomes B0 by 1 minus P whole square, that is equal to 1. So we can say that B0 is equal to 1 minus P square. This is one relation. Another condition is omega is equal to pi by 4. So what is the transfer function? So it is 1 minus P square. In place of B0 we write 1 minus P square, and 1 minus Z inverse square was the original equation, 1 minus Pz inverse. So in place of Z we write e to the power j omega, where omega is pi by 4, and Z inverse is there, that's why it is e to the power minus j pi by 4 overall square. So it is 1 minus P whole square, then 1 minus P cos pi by 4, then in place of e to the power j minus pi by 4 we write this, and we finally get that 1 minus P whole square divided by 1 minus that cos square pi by 4 plus sine square pi by 4 is equal to 1. Okay, and it is sine pi by 4. No, we are just putting the values of cos pi by 4. It is 1 by root 2. Okay, and sine pi by 4, it is 1 by root 2. So if you take the magnitude square, it becomes 1 minus P whole to the power 4 and 1 minus P by root 2 whole square plus P square by 2 whole square, because it is a, if it is what? It is magnitude square, that means it is A square plus B square. Okay. So we get that is equal to do you understand this expression?
Yes, sir.
How it is coming? This expression from this to this?
Sir, we are multiplying 1 by p whole square on the denominator and numerator.
No. We are taking magnitude square of this part. Okay. So if you take the 1 minus p by root 2, okay, whole square. First, a plus, say it is a plus jb, like that. A plus jb whole square. Okay. So a is 1 minus p by root 2 whole square, and you try to calculate yourself. First, this one you calculate denominator. Okay, denominator, then उसका square होगा 1 minus p by root 2 whole square plus हाँ, उसका स्क्वायर लो, उसके बाद रियल रूट ओवर रियल स्क्वायर प्लस इमेजिनरी स्क्वायर करो. ठीक है, 1 minus p by root 2 whole square plus 2 into 1 minus p by root 2 into j into p by root 2 plus is a plus b whole square. First you apply plus jp by root 2 whole square. Jp by root 2 whole square. So it becomes 1 minus p by root 2 whole square plus minus j square is there, so it is p by root 2 whole square plus 2 into 1 minus p by root 2 by p by root 2 into j. So it has you have to take the magnitude. Okay, magnitude, if you take the magnitude, that times it becomes root over real part squares plus imaginary part squares. Okay, so if you take further simplify, then you will get this expression. Understand? Are you doing it?
Yes, sir. 1 minute, sir.
डिनोमिनेटर का रूट ओवर रियल पार्ट स्क्वायर प्लस इमेजिनरी पार्ट स्क्वायर, और वो कैंसिल हो जाएगा, एक टर्म कैंसिल होके ये आएगा 1 minus p by root 2 whole square minus 2 into 1 minus p by root 2 into p by root 2 plus वो 2 into 1 minus p by root 2 into p by root 2, वो वाला पार्ट कैंसिल हो जाएगा, -2ab plus 2ab ये कैंसिल हो जाएगा और बाद में तुमको मिलेगा 1 minus p by root 2 whole square plus p square by 2। तो कैलकुलेट करके देखो, ये आएगा। आ रहा है कि नहीं? आ रहा है? नहीं तो हम वीडियो ऑन करके दिखा देते हैं। Anybody has done?
Sir, I tried, sir, but I'm getting some digits extra there.
Okay, I'm showing you. Just you can take the snap. Let me stop it. Okay, just you see this calculation. Okay. Is it visible or not? I don't know. ये जो पार्ट है, first you calculate a plus b whole square. So a is 1 minus p by root 2 whole square into 2 into 1 minus p by root 2 into j into p by root 2 plus j into p by root 2 whole square. Okay. Now there you will see that this has real part as well as imaginary part. So just combining, gathering to the real part, that is 1 minus p by root 2 whole square minus p by root 2 जो है minus p by root 2 whole square. This is real part. And imaginary part is 2 into 1 minus p by root 2 into p by root 2 into that j. Okay. So take the root of square of real part square and imaginary part square. Now again in real part, okay, again in real part, you will see this is also a minus b whole square term is there. Okay, a minus b whole square, because it is root over of real part square. So a minus b whole square. Okay, so it is 1 minus p by root 2 whole square. Okay, into 2 into 1 minus p by root 2 into p by root 2 minus a minus b whole square. A minus b, individual they are square term, but it is a square minus b square whole square kind of term. Okay, 1 minus p by root 2 square minus p by root 2 whole square, उसका स्क्वायर है, तो उसका स्क्वायर करेंगे तो क्या होगा, a स्क्वायर माइनस 2 इंटू ए इंटू बी, और ये और वो कैंसिल हो जाएगा और लास्ट में ये पार्ट रहेगा जो स्प्रिंग में है। ये एक बार ट्राई करके देख लेना, ठीक है?
Yes, sir.
ओके, इस स्क्रीन में आ रहा है, यहाँ पे हम हो सकता है ये हो गया। अच्छा, इसके बाद क्या है कि ये स्टेप जंप करके लिखा है, फिर देन व्हाट वी गेट, दैट रिलेशन इज, so this is equal to half, that means magnitude square, मैग्नीट्यूड जब किस चीज का लेते हैं तब वो हो जाता है रियल पार्ट स्क्वायर प्लस इमेजिनरी पार्ट स्क्वायर, बोथ न्यूमरेटर एंड डिनोमिनेटर में, रूट ओवर रियल पार्ट स्क्वायर प्लस इमेजिनरी पार्ट स्क्वायर इन न्यूमरेटर डिवाइडेड बाय रियल पार्ट स्क्वायर प्लस इमेजिनरी पार्ट स्क्वायर इन डिनोमिनेटर, और उसका स्क्वायर लेंगे तो वो हाफ हो जाए, उसके साथ इक्वल करना होगा हाफ। So then here we will see that we get equation of P that satisfies P is equal to 0.32 So finally we get the transfer function as, according to this, B0, putting the value of B0 and P. So we get B0 is 0.46 and P is 0.32 Z inverse square. ये एक example है. So the same principles can be applied for the design of band pass filters. What is, so low pass filter design कर लिए हम लोग, एक एग्जाम्पल लेके. अभी बैंड पास कैसे करेंगे? So basically the band pass means what? There is a range of frequency in which gain is there, and outside that gain is 0. So within pass band, gain is some significant value. So at the two frequencies, limiting frequencies, okay, so gain should be falling or 0. So उस लो पास फिल्टर को हम लोग अगर थोड़ा मॉडिफाई करेंगे उसका ट्रांसफर फंक्शंस बाय एडिंग पोल्स ऑफ कॉम्प्लेक्स कॉन्जुगेट, देन वो फिर वी कैन डिजाइन that filter, band pass filter. So complex conjugate मतलब सिंगल एक कॉम्प्लेक्स पोल ले सकते हैं, लेकिन कॉम्प्लेक्स कंजुगेट इसलिए लेते हैं कि when we multiply the poles in the transfer function, then the coefficient arising out of that multiplication will be real number. इसलिए फिल्टर डिजाइन आसान होगा. हम लोग जब फिल्टर डिजाइन करेंगे या करते हैं, सो हम लोग कांस्टेंट वैल्यू दैट शुड बी रियल वैल्यू लेते हैं. सिर्फ एक कॉम्प्लेक्स पोल लेने से भी काम हो सकता है, लेकिन कॉम्प्लेक्स कॉन्जुगेट लेने से क्या होगा, फिल्टर कोएफिशिएंट रियल होगा. ठीक है, अभी एक एग्जांपल देखते हैं. डिजाइन अ टू पोल बैंड पास फिल्टर with the filter that has center of its pass band at omega is equal to pi by 2, 0 in its at omega is equal to pi by 2, 0 in its frequency response characteristics at omega is equal to 0 and pi, and magnitude response of 1 by root 2 at omega is equal to 4 pi by 9. Okay? So इसमें बोल रहा है कि एक पास बैंड रहेगा जिसका सेंटर फ्रीक्वेंसी है पाई बाई 2 में, ओके, और 0 रहेगा कहाँ पे, कॉर्नर में, दोनों लिमिटिंग फ्रीक्वेंसी, मतलब जहां पे गेन 0 हो जा रहा है. 0 in its frequency response characteristics at omega is equal to 0, मतलब lowest frequency, and omega is equal to pi, it is highest frequency. ये टोटल फ्रीक्वेंसी रेंज है 0 to pi में. तो उस दोनों फ्रीक्वेंसी में गेन 0 हो जाएगा क्योंकि वहां पे 0 प्लेस करना है उस फ्रीक्वेंसी में. ठीक है, और ओमेगा इज इक्वल टू पाई बाई 2 में पास बैंड है, मतलब गेन है, तो उस फ्रीक्वेंसी में क्या प्लेस करना होगा, 0 प्लेस करना होगा कि पोल प्लेस करना होगा. कैन एनीबॉडी टेल? जिस फ्रीक्वेंसी में गेन है, द फ्रीक्वेंसी एट विच द गेन इज हाई, we have to place poles what?
Sir, pole.
Pole. Okay. So So this is the specification given, and another specification is given, that is magnitude response of 1 by root 2 at omega is equal to 4 pi by 9. So ओमेगा जब फ्रीक्वेंसी 4 पाई बाई 9 है तब उसका गेन बोल दे रहा है 1 by root 2 होगा, ठीक है. So with these characteristics we start our design. So first we have to define the poles. How many poles are required? What is there in question? How many poles are there?
Sir, 2 poles.
2 poles. So 2 poles and frequency is omega pi by 2. Okay. So and the pole should be complex conjugate because filter coefficient then will be real. So we consider 2 poles P1 and 2 at frequency R into e to the power j pi by 2. Pi by 2 hai because omega is pi by 2. At this frequency it should have gain, that is center frequency of the pass band, maximum gain or constant gain, whatever it is. So omega is pi by 2 and poles is considered because it is z, values of z. So z is equal to R into e to the power j omega. It is your formula. So in place of omega we write pi by 2. So we get 2 poles at R e to the power plus minus a complex conjugate. Complex conjugate pole should be there. So it is j pi by 2. So this is one criteria. Another criteria is the zeros. Okay. Zero in its frequency characteristics at omega is equal to 0 and omega is equal to pi. So he at these two frequency, gain should be 0. So what should be the value of zeros? Can anybody tell? At this two frequency, omega is equal to 0 and omega is equal to pi. क्या होगा जीरो का वैल्यू?
One and minus one.
1 and minus 1. Okay. 1 and minus 1. Who told 1 and minus 1? MS कौन है?
Sir Shashank.
Shashank. Okay. So we get z is equal to 1 and minus 1 corresponds to omega is equal to 0 and omega is equal to pi. So we have defined the zeros and poles and putting into the transfer function with arbitrary gain g and pole 1 and z is equal to plus 1, zeros at z is equal to minus 1 and z is equal to plus 1, and poles at z is equal to minus jr and z plus jr. Can anybody tell?
Sir, they are the poles.
They are the poles, but how we are getting it?
Sir, by substituting, if we keep the value r into e power plus or minus j pi by 2, then we will get it, sir.
Yes. Cos pi by 2 plus j sin pi by 2. Sin pi by 2 is 1. So it is j into r. So Z minus JR into Z plus JR. So this is J into Z square minus 1 divided by Z square plus R square. Now next, so we are told that at pi by 2 gain should be 1. Okay, so at pi by 2 we are putting what at the right side I have written that in this term, in this expression, okay, you in place of Z is equal to e to the power j omega. Okay, Z is equal to e to the power j omega, and omega is equal to pi by 2. We get the value as Z is equal to j. Okay, so we put the value of Z is equal to j. So we get j square minus 1. Okay, in this, according to this equation, z square minus 1. So it is j square minus 1, and in the denominator it is z square plus r square. So it is, in place of z we write j. Okay, so value of z at omega is equal to pi by 2 is j. So it is j square plus r square. So we get minus 2 g into minus 2 divided by minus 1 plus r square. So that's why it is coming, this one, g into 2 by 1 minus r square. That should be equal to 1. Okay, so we get g is equal to 1 minus r square divided by 2. Okay, now another condition is that at omega is equal to 4 pi by 9, it should be, the gain is 1 by 2, the magnitude square gain. So magnitude square लेंगे तो हाफ हो जाएगा, 1 by root 2 का स्क्वायर करेंगे तो हाफ होगा. तो ये हाफ हो जाएगा कब, जब frequency is 4 pi by 9. Now in the same equation we write in the place of values of z, that is z square. Z square is there, you see, the z square minus 1 z square plus r square. So if it is z square, so it should be e to the power j into 8 pi by n, because frequency is 4 pi by n, so it is square is there, so it is 8 pi by n minus 1 divided by e to the power j 8 pi by n plus r square. So now splitting into real and imaginary part and combining it, so you get this expression. Now after this, if you calculate the mod magnitude of hz square of this equation, you will get root over real. You have to calculate root over of real part square plus imaginary part square in both numerator and denominator. So finally you will get this expression. Okay, that is equal to half. So this thing is not calculated shown here, but you should do yourself to clarify it. So finally you will get the values of r square, it is this, and if you put those values, all those values of g and r, okay, you will get this transfer function of hz, this one. Okay, that is a band pass filter transfer function. Okay, and its characteristics, you see graph is this one. You can see that gain is maximum at the frequency pi by 2, which is desired, and certain band of frequency within 0 to pi is considered, where we are getting certain gain. Okay, so this is the methods to how to design low pass, high pass and band pass filter or frequency using pole and zero locations. Okay, so but this method actually it is not that much very accurate. Okay, and also some other complicated nature of frequency band is there, so those cannot be treated with this method. But this is a very good concept that how it filter is designed using poles and zeros. So from the tomorrow I'll discuss some few topics, and then first module will be over, and there will be first quiz in the second next week. On any day it can be conducted in the evening. Okay, so be prepared for the quiz. It will be conducted in the next week on any day evening. So your Vishal Shah is the coordinator. He will give you the link. So
Sir,
here I yes.
Sir, you inform the quiz date, sir, because the other subjects quiz we will arrange according to that.
Okay, it will be provided. It will be announced.
Yes.
But for the timing, I am informing you that quiz will be in the next week. Okay.
What will be the pattern of the paper?
Pattern will be objective, purely objective. Okay. Okay, now you may leave.
Thank you.